Hello everyone. The objective of my research is to compensate the muscle dysfunction during a gait protocol using a control algorithm by comparative analysis between healthy and constrained muscle function. The test group consists of 10 women between the ages of 22 and 28 with height and weight in a specific range. The trajectories were simulated with limitation using a commercial knee brace and adjusting the number of springs, obtaining signals from three muscles: rectus femoris, tibialis anterior, and gastrocnemius lateralis. For simulate constraints 1, one spring was set. For simulation 2, two springs, and for simulation 3, three springs. In general, the research focuses on three main pillars: signal acquisition and processing, constraint identification, and trajectory compensation according to the type of constraints detected. The higher the degree of limitation, the smaller the increment that can be applied in the trajectory of progressive recovery of normal gait. The maximum and minimum angular range of motion of each limitation are presented for progressive consideration during recovery therapy. The following is obtained: the normal trajectory of the knee joint and the trajectory of each limitation, 1, 2, and 3. An artificial neural network is responsible for identifying the level of gait limitation of each test subject. The inputs to the network are data extracted from the potentiometer signals and the EMG signal on the three muscles. To each signal, a discrete Weyl transform is applied for correlation. Then, 8 discrete Weyl transfer coefficient will be the input values of the A and N. For training, the output of the A and N will be the binary code for the four gait types, as shown in the table on the left. Now, in the network, we have the following configuration, taking into account that for each subject in the test group, 4 signals were taken, corresponding to the muscle and the knee joint angle, and that the subject can be classified into 4 classes. A vector is constructed whereby each subject labeled with a class has 32 features, which is 2 product of the A coefficient of the 4 signal sources. The neural network is configured in such a way that it yields an accuracy of 90% in the classification of constraints. In the table on the right, the evaluation metrics were obtained from the confusion matrix. Once we have identified the type of limitation of the person, this data is now the input of the control system that will generate the compensation trajectory by increasing the angular trajectory by a small percentage allowed. For the adaptive control system, we have the planned model, which must support the trajectory according to the percentage already identified. An equation is generated that considers the torque generated by the person's leg and that of the motor. The control is a PID where the values of the coefficient were calculated at simulation level. As an adaptation mechanism, a fuzzy control with trapezoidal response is proposed, configured in the best way to reduce the error, like shown in the table, and generate a smooth but progressive trajectory. Like conclusion, we have an average accuracy with this AMN model. Sufficient reliability is provided to know where the gait shows some limitation and to subsequently apply strategies for progressive recovery through robust device and control. The control strategy shows satisfactory results because ENG and knee position signals make it possible to identify gait limitation and to establish trajectories with a safe increase that can be used for normal gait recovery. And the contribution is a control model correlating electrical activity characterized with a DWT and lower limb angle with different levels of constraint using an artificial neural network.
Thank you very much.